I don't pay attention to it. I don't want it as cause an issue for people.
Yeah, I'll actually
There you go. The further up to the front you are, the easier it is to see over you. So.
Yeah. Ah, so I should always do the remote, right? Yeah, the photograph principle, which I just instinctively go to the back and go
To what?
the photograph principle.
We do it?
Yeah.
We do?
I think we can go.
All right, that's excellent. All right, thanks for coming today for this new lunchtime talk. Before introducing our speaker, let me remind you of the events in the coming days. Next week on Tuesday, we're going to have a talk by Porter Williams, who is right here. Looking forward to that talk called the Aim and Structure of Cluster Decomposition. The title hasn't changed. All right, so now we know. And on Friday next week, there is no lunchtime talk, but we have the first lecture of the annual lecture series given by Thomas Reichmann on Niels Bohr, Transcendental Physicist. So that's a program for the coming days, sort of philosophy of physics, as you can see. But it's not intentional. Sometimes just the chips fall this way. So anyway, this is the way it's going to be. Today, it's my great pleasure to introduce Feraz Azhar, who is assistant professor at Notre Dame. Feraz got 2 PhDs, so it's a doctor, one in philosophy at University of Cambridge, and one in physics at the University of California, Santa Barbara. He works in many areas in the philosophy of physics, but has interest in cosmology. And it's a role of probabilities in cosmology. He has published extremely widely. I've been told to try to embarrass him as much as I can. So, it's published widely in the best journals in the field. It's published in Erkenntnis, in studies, in also places like Physical Review, Foundations of Physics, and so on and so forth. It's quite a long CV if you look at the list of publications. And today we are very lucky to welcome for the first time, and hopefully not the last time, here at the center. And Feraz is going to be talking about rethinking the Anthropic principle.
Thank you so much for the very, very kind introduction. It's a thrill to be here and to have the opportunity to tell you about work that I've been engaged in over the course of the last couple of years or so. This is work that is done in collaboration with Niels Linnemann. This is one of the projects that we're working on. This is the first cab off the rank. And the idea is to, as the title of the talk suggests, to look deeper at the anthropic principle, to try to get a sense of what it is that this principle means, what it can mean, and how it is that we might go about applying it. So this talk is based on a forthcoming paper with Niels at the same time. So the anthropic principle has been around for 50 years or so, and it's been implicitly used for longer. Here is Brandon Carter in 1974. Here is his statement of the principle. What we can expect to observe must be restricted by the conditions necessary for our presence as observers. So there's a lot here, and I'll say more about each piece in a moment. What I want to do at the outset is to set the scene a little bit. One thing I can say that is true about this particular principle is that it has been controversial for its entire life. It has been described as unscientific and yet a remarkable device. There are weaker versions of the principle which have been described as virtually trivial. Here is local hero, global hero, John Ehrman saying it's a corollary of a truism of confirmation theory. There are stronger versions of the principle that are logically risky. There are, there's that particular stronger version that Macmillan has in mind, if it's construed in a certain way, leads to, according to Frank Wilczek, irrational mysticism. And yet, I contend the principle has been useful. It has arguably been very useful in a couple of different settings, and I'll tell you about those in some detail. So there are two reasons for the controversy, I think. There are 2 reasons why the anthropic principle has been maligned and misapplied. It has been maligned because it was misapplied. It has been maligned even when it has not been misapplied. The two reasons are that it is unclear in physical settings to what certain terms of the principle should refer. And I will go through these various terms and try to clarify the issues at play. And secondly, it is unclear, even assuming that you know what these various terms mean, to what ends the principle should be applied. How do we, in fact, use it appropriately? So I personally have a methodologically conservative position on the second issue, except for when it's the case that you're dealing with multiverse cosmological scenarios. So I won't quite be talking about those, but I'm happy to do so. I'm going to focus on more terrestrial considerations, or more local considerations, although those considerations are rather global anyway. Okay, so one reason there is a misunderstanding, or misunderstandings can arise, is because of the existence of this phrase. In red, our presence as observers cannot be uniquely interpreted in the context of the theories within which this principle is meant to be understood and applied. There is a theory in the background that I think you ought to advert to when you're thinking about this principle, when you're applying this principle, and the idea is that our presence as observers is ambiguous in that context. What are those current best physical theories? Well, I think they are effective theories, very broadly construed. So these are theories that have a limited regime of applicability, a regime that's typically delineated by a range of energy or length scales. I don't just have in mind things like effective field theories or quantum field theories understood in that particular way, but I have in mind all the kinds of theories that we look to write down in the context of astrophysics, astrobiology, biology, potentially even neuroscience, so a broad sweep, as it were. Making sense of this kind of construction, I think, is tricky in certain circumstances. Nonetheless, it's plausible that all of these theories have a limited regime of applicability. And from that point of view, I consider them to be effective. And these are the kinds of theories that we have at our disposal to try to make sense of various terms in the anthropic principle, and maybe more generally too. So what is it that our effective theories can actually tell us if they can't tell us what it means to describe our presence as observers? The thought is what our effective theories can describe is our observational situation. And that this needs to be put front and center when you're thinking about the anthropic principle. So therefore, I think one needs to reformulate the anthropic principle along the lines that I will go into in some detail. The principle, the reformulation of the principle, I'm going to dub the effective observation principle. And in this principle, our observational situation is understood in the context of these theories, is placed front and center. What is important for understanding and applying, and what I think is the intended content of the anthropic principle, is an observational situation within which we, as observers, arise as an accident, as a contingency. We are accidents from one point of view, if you stare at these theories hard enough. This is the thought, and what we personally can expect to observe relates to this observational situation out of which we arise as an accident, and not specifically to us as observers. Okay. So how do you go about characterizing your observational situation, right? What do we mean by this? This is the central part of the analysis, and I'll get to that in a moment. Let me say a couple of things, a couple of caveats that will give you a sense of the scope of the remarks that I have in mind. Firstly, this effective observation principle, the statement of it, and how it is that you go about applying it, this is not an entirely new type of anthropic style reasoning. The goal here is to present and defend a precise formulation of the anthropic principle. Let's try and make this principle precise. So as I've said, I endorse a methodologically conservative position on the ends to which this principle should be applied. What this principle is telling you is it's telling you to beware of selection effects. Beware of selection effects, features in the thing that you're observing that are not intrinsic to the thing itself, but arise as a result of the means of observation. Beware of those in your reasoning. That is what it is saying. And that is what the effective observation principle is also saying. The anthropic principle and the effective observation principle, neither of these principles are explanatory in the traditional sense. When you use anthropic reasoning to successfully predict or post-predict the value of some observable, what it does is that it explains away our surprise about the value that's obtained. Ehrman said this in 1987 very clearly in describing a weak version of the anthropic principle. It explains away your surprise. It doesn't, capital E, explain. Okay. So the thought is that there might be a more standard story to be told for why the value that the observable that you're interested in takes the value that it does. Where the story is somehow more explanatorily powerful, more traditional than the account that's provided by the anthropic principle or by the effective observation principle. And I think this particular position about the nature of the explanation that is provided by the principle, I think this is consistent with suspicions about the anthropic principle, which arise from its seeming departure from these usual explanatory goals in science. And yet, I still think the anthropic principle and the effective observation principle can play a non-trivial role in our theorizing about physical settings very generally. All right, so here is what I want to do today as an overview. Firstly, I want to tell you about Carter's intended meaning, what he meant by the anthropic principle. Then I'll introduce this effective interpretation. A centerpiece of that is telling you precisely what it is that I mean by an observational situation. I then want to address a particular question that arises in thinking about anthropic principles very generally, and then I want to ask that question in the context of the effective observation principle, namely, how anthropocentric is the anthropic principle, and so therefore also the effective observation principle. How central are observers to the statement of the principle and to scenarios in which we use the principle? Then I'll apply it. So I will in fact rework and show you Carter's original definition, sorry, not his definition, but the description of when he applied it first in 1974, and reanalyze that particular analysis in the context of the effective observation principle. So this will be done in two settings, in two ways, by a non-probabilistic analysis and a probabilistic analysis. And what I want to stress is that I think what has in fact been successfully applied in these kinds of scenarios when the anthropic principle is putatively applied is the effective observation principle, possibly in all circumstances in which the anthropic principle has been applied. The principle I have in mind is the principle that has been, in fact, applied. And it has been applied with a specific observational situation in mind, a specific context-dependent, theory-dependent characterization of one's observational situation in mind. Then I want to go beyond, quote unquote, cosmology, namely, I want to discuss applications of this principle that lie, so within the cosmos, as it were, but outside of cosmological considerations. So the idea is that there are local applications of the anthropic principle that relate to nuclear physics, for example, that one can get off the ground in the context of the anthropic principle, and you can rework those particular examples via this effective methodology as well. So the anthropic principle is also used in the context of, for example, nuclear physics. And although I won't go through that example, you can certainly read about it in the paper. Okay. Cosmology is rife with principles. They're all over the place. There's the Copernican principle, the cosmological principle, there are indifference principles, there's the anthropic principle, there are weak versions of the anthropic principle, there's a strong anthropic principle, there are strong versions of the strong anthropic principle. There are many principles. And the reason for the existence of these principles, I think, is very similar to the reason why they might exist in other areas of philosophy and other areas in physics. And my short take on it is that there's an entity of interest here, the entirety of the universe, and there's a certain epistemic access that we have to this entity, and there is a bridge between those two things. And principles help us bridge this divide between these two ideas. And so, between the thing that we're interested in and what we in fact have access to. And here's McMullen saying basically the same thing, but more eloquently. It is hardly surprising that cosmological invention should have been guided as much as it has by principle. Theorizing about the universe requires a long stretch beyond the relatively safe routines of inductive science, expectations as to what sort of order we should expect to find, or alternatively as to what should, at the cosmic level, count as order, are bound to dominate. Indeed, they have. Okay. Carter's version of the anthropic principle is some sense of pushback on a souped-up version of the Copernican principle. The Copernican principle being the idea, roughly speaking, that we are not privileged in any way. Copernicus taught us we're not central, right? Pushing back against Ptolemy, you could take that and soup that up and think, well, there's no sense in which we are privileged in any way. Carter comes along and says, look, our situation is inevitably privileged to some extent. This is part of one way to think about motivating the anthropic principle. So let's go through it. What we can expect to observe, that part of the anthropic principle is referring to us as people going about the world, performing experiments, trying to make sense of confirmation. Observations relate to experiments that we do, and there's a kind of natural distinction that one could draw between different kinds of observation that Carter does in fact draw, and I think it's useful for cosmological theorizing. The distinction is as follows. You might have the observation relate to our spatio-temporal position in the universe and or our parameters or initial conditions of our physical theories. So in the first case, you might be interested in where in the universe we could possibly arise from a spatio-temporal point of view. You fix the parameters, you fix the initial conditions, and you ask precisely where in space could I arise, or when in cosmic history could I arise? If you are asking that kind of a question, you are probing the weak anthropic principle, which is as stated, what we can expect to observe about our spatio-temporal location within our universe must be restricted by the conditions necessary for our presence as observers. We cannot be too far away from the sun. It is too cold. We cannot be too close to the sun. It is too hot. If you use this kind of reasoning to ascertain a kind of Goldilocks region, then you have implicitly employed something like the weak anthropic principle, where you have fixed various parameters and you've asked questions about your spatio-temporal position in the universe. The other question you can ask relates to parameters and or initial conditions of our physical theories. So this is a strong version in the sense that it's extended, but it's not strong in the sense of the sort of implication from this to other kinds of principles. So if you want to ask questions about what happens when I vary the cosmological constant, you're in the bit where you have in mind something like anthropic star considerations, then you are involving yourself in a deployment of the strong anthropic principle. What we can expect to observe about the values of fundamental parameters in our cosmological theories, like lambda, the cosmological constant, like the curvature of spatial slices in the context of FLRW situations, and or initial conditions. If you're interested in those, the values of those things, you're involving yourself in the strong anthropic principle if you are assuming that what you can expect to observe about them must be restricted by conditions necessary for our presence as observer. These two principles are saying the same thing. They're just applied to different kinds of things, right? They're both expressing the idea that one ought to be aware of selection effects. Here's a picture, an illustration of how you can in fact make sense of this. Imagine of the kind of selection effect in play. The idea is that I have two possible parameters that I could measure. The anthropic principle tells you that, look, here are the conditions that are necessary for the presence of observers. You're going to see one of them if you go out and perform this measurement. You cannot see anything outside of this green region. These are necessary conditions. They're not sufficient. If one of these particular points in this green square obtained, it doesn't mean you're necessarily going to arise. Okay? It doesn't guarantee that you arise. Can you do better is then the question that arises than necessary conditions. Can we do better than just necessary conditions? And we might be able to, but we don't have the theory at our disposal to do so just yet. So the idea is that any such principle like this should be understood in the context of our current best physical theories, and in such theories, the notion of an observer, as I said, cannot be made precise. What we can describe are broadly interpreted conditions that would likely preclude observers, that would not lead to observers as we might qualitatively understand them. We can say that to some degree with certainty, although there are questions about how well we can do that as well. Okay. So with this in mind, here's the reformulation. So the reformulation of the anthropic principle takes the thing that is ambiguous at some level and replaces it with a physical entity that can in fact be described in the context of our physical theories, with respect to which observers like us might arise. And so we replace this particular phrase with a placeholder. That placeholder is an entity that can be described expressed within the context of an effective theory, namely, or maybe multiple such theories. There are rules that secure a correspondence, is what I mean, between the entity and physical states and or conditions of the theory. So our presence of the observer is out, delta in. What is delta? Our observational situation. How do we understand it? That's tricky, but I'll try to make sense of that in a moment. Okay, so given the idea is that given that delta is instantiated, observers as we qualitatively understand them may arise. The underlying effective theory is going to depend on the situation of interest, on the subsystem that you're interested in. If the subsystem is the entire universe, then the theory of interest is going to correspond to a cosmological theory. If the subsystem of interest is a nuclear model, then you're going to be using models of nuclear physics to try to make sense of it. Here is an example of delta. It's a bit of a mouthful. Energy density perturbations on spatial slices, very early on in the history of the universe, which are drawn from some statistical distribution. Small differences in energy density from place to place, very early on. This is the kind of thing out of which observers could possibly arise. Doesn't guarantee that they're going to arise, but it's certainly something that is expressible in the context of our effective theories. Now, this particular characterization of our observational situation might not, in fact, strike you as a very good one, right? And at some level, it is not a very good one, because it's not going to do a good job of constraining our observations. And so the challenge that remains is in trying to employ the effective observation principle is that of finding relevant deltas that yield suitably precise constraints in the particular situation of interest. And I think it's doubtful that one can, in fact, generate relevant deltas algorithmically. It's context dependent, it's theory dependent. There's a bit of an art, I think, to determining precisely what delta might be in a particular situation. But I think you can generally characterize it, and here are some ways to think about generally characterizing delta, namely our observational situation. As I've said, it needs to be expressible in terms of the theory. Delta can be multiply realized. So assumptions and results in cosmology and astrophysics are often expressed in terms of aggregate properties, such as statistical properties, which can be realized by multiple combinations of parameter values and or values of initial conditions. So Gaussian energy density, but little differences in density from place to place can be encoded in space-time in lots of different ways. Lots of different point-by-point specifications of the energy density are going to yield Gaussian energy density perturbations at a very early time. Energetic degrees of freedom in space-time that satisfy certain energy conditions, such as including the energy density is non-negative. These are consistent with various possible values of parameters and or initial conditions. There are multiple candidate ways of describing our observational situation. There's lots of them. Here are 4. You could think about our observational situation as corresponding to a low entropy initial state. Or we could think about it as corresponding to Gaussian energy density perturbations at some early time. If you have a particular count of complexity in hand, which I've denoted by C, then a precondition, a necessary condition for complexity might also be a way of thinking about your observational situation. So a precondition for complexity is understood in the context of some specific theory of complexity or some specific account of complexity is another kind of candidate way of describing an observational situation. Then, of course, there is the actual account of complexity itself that you may have in hand. That might sound like a reasonable way to describe the situation that we find ourselves in, out of which we might arise as an accident. Still, depending on the level of detail that your theory of complexity has. Nonetheless, okay, so these are 4 different possible candidate deltas, and the question is, how do you select from amongst such candidates? Taking into account there might be relationships between them. I think a sensible principle here to involve, it's not quite something like the requirement of total evidence, but it's that you should select the entity that is specific as possible about our observational situation. Choose the most specific delta you could think of that is indeed expressible in terms of the theory. So the reason for this, I think, is that it's really for the predictive and descriptive power, how well you're going to be able to constrain the variable of interest ultimately. So imagine you have a version of this principle. Okay, good. So a version of this principle which says what we can expect to observe must be restricted by the conditions necessary for complexity to arise. Compare that with a version of the principle which takes complexity and replaces it by matter and antimatter asymmetry. This second option seems a lot less useful from the point of view of what we can expect to observe is going to be better constrained by the theory of complexity, or the account of complexity that we have in hand compared to the second version here. Okay, so this is what I want to say about delta. I think there is still an issue here about how it is that you go about actually describing how you hit upon it in any particular situation. As I've said, I think it's a bit of an art form to it. Nonetheless, there are broad things that you can say about it, and I've covered them just now. What I want to move on to is this question that I mentioned at the outset, this question about anthropocentrism in the effective observation principle. Namely, to what extent should we consider this principle to be anthropic, to be human-based, human-centered in particular? Humans aren't unambiguously expressible in terms of our effective theories, and I think they cannot therefore be central to the nature, they cannot be central to this effective observation principle. But I think it's still via considerations of conditions that are somehow relevant for humans and observers more generally that we go about choosing a suitable delta in a particular situation. So EOP is relative to some class of observers in some sense, a class that's going to contain humans. It's going to contain beetles and brainy dinosaurs and whatever else people have put out there. But it's not so specific about exactly what that is, because our theories cannot be. If you demand that this principle needs to account for totally different types of observers, to the ones that different to any one that we possibly witnessed ourselves or could imagine, then I think that the effective observation principle and anthropic reasoning more generally will be rendered vacuous. So here is a condition that is probably consistent with lots of different types of observers, namely slight inhomogeneities in the very early universe, that delta that I mentioned earlier. Carr and Rees in a Nature paper 1979 say that thermal disequilibrium is one thing that they can guarantee as the kind of thing that could give rise to lots of different types of observers. It's the kind of thing that needs to be in the background. But then I think the power of this principle is significantly compromised. I don't think one can do a good job of constraining things that you might be interested in as a result of this. Okay. So I want to move on to applying the effective observation principle. So it happens to be the case that despite the lack of clarity about what the anthropic principle refers to, or what various aspects of it refer to, it has been successfully applied in a variety of physical settings. It has in fact done a good job in certain settings, and I want to work through some of these applications. And also what I want to show you is that what has in fact been applied is an instance of the effective observation principle with a specific context-dependent, theory-dependent choice for delta, the observation in these original applications, and in fact in other applications as well. So Carter's analysis in his 1974 paper is of a large number of coincidences. There's a coincidence that was noticed that I'll tell you about in a second, and by applying the weak anthropic principle, Carter gets around the need to invoke non-standard physics. In particular, Dirac looked at this particular coincidence and thought that it was evidence for the idea that Newton's gravitational constant in fact varied with time. A non-standard theory. Certainly non-standard relative to the Big Bang model of cosmology that was forming, that was around at the time. And Carter said, in short, you don't need this non-standard theory. This coincidence is just the result of a selection effect. And then he calculates for you, in the context of the standard Big Bang theory, how it is that this coincidence can arise, thereby getting around the need for this exotic theory. So Carter does this by identifying proxies for the presence of observers, proxies for observers. Then he describes the link between these proxies and our spatiotemporal location, and he derives a constraint on our spatiotemporal location. And if the constraint then allows you in general to account for the coincidence, then you're done. You can get around Dirac's theory. Here is the coincidence. And if you've never seen this before, ask yourself whether you would find this surprising. The coincidence is that the size of the observable universe today, divided by the size of an atom, is on the order of magnitude of the electrical force between elementary particles divided by the gravitational force between elementary particles. Knew nothing else and you stared at that, would you be surprised by that? Some say no, some say yes. So, the order of magnitude of this agreement, so that's one issue. But the actual value of both of these terms is roughly 10 to the 40. And the question is, why is this the case? So from this particular coincidence, you can derive that equation that I have for you below. T naught is the current age of the universe. That's going to come into play in terms of thinking about the size of the observable universe today. And it's related to the inverse of the cube of the mass of a proton. These are units that have been chosen, in which G equals H bar equals C equals K to 1, I think. If you reinsert the most important parameter here, G, it appears as G inverse on the right-hand side. So if you really think these things shouldn't be related to one another, this time T naught shouldn't be related to, for example, the right-hand side, you might think this relationship holds for all time. You might look at this relationship and think and say, oh, maybe G varies as 1 over T. And if it varies as 1 over T, then it guarantees this. And it gets its force insofar as you think these things might not be related to one another. This was the motivation for Dirac's variable G theory of cosmology. Carter comes along and says, no, this is the outcome of a selection effect. If you apply the weak anthropic principle, you can derive this in the context of our current theories of cosmology. So Carter assumes that the age of the universe today is an age that corresponds to the observer era. So T naught is of the order of magnitude of the typical amount of time the star undergoes hydrogen burning to produce helium in its core. The amount of time that a sun can generate mild, nice conditions in which observers could in fact arise. So why would you think that T naught is of that order of magnitude? If it was significantly less, if the age of the universe was significantly less than that intrinsic stellar lifetime, then heavier elements would not have formed, and heavier elements are thought of as necessary for the presence of observers. If T naught is significantly larger than that time, then our galaxy, Carter reasons, wouldn't have very many stars left in it, and the stars it would contain wouldn't have sufficient energy output. And this would be necessary for observers too. So then Carter then goes ahead and calculates, using some basic astrophysical arguments, that this intrinsic lifetime is 1 over the cube of the mass of the proton, with G inverse on the right-hand side. Done, right? That gives you that equation, that T naught goes as that function in that way. A single constraint on the current age of the universe is derived. The upper and lower bounds are only distinguished conceptually for Carter. Successful application of the anthropic principle, right? In this application, nothing like an observer has been uniquely singled out in Carter's argument. Neither of the proxies that are assumed in Carter's calculation are proxies for just an observer, let alone for, as stated in the weak anthropic principle, our presence as observers, and so it's not clear that the weak anthropic principle has been applied. All sorts of physical states could be substituted for the notion of an observer, and you would get the same answer. You would get the same value for T naught by Carter's reasoning. What has been identified are two ways of thinking about our observational situation. Delta 1 is heavy elements, and delta 2 is heavy elements and sufficiently energetic stars. Conditions for which are indeed expressible in terms of our theories of cosmology and astrophysics. And it is in that context that you can put the anthropic principle to work. And it was put to work in that context. And that is naturally, I think, an application then of this effective observation principle with some sort of notion of delta in hand, something like heavy elements. Okay. Let's move on to a probabilistic account. So this account is what John Ehrman set down in 1987. There are precursors to this. Barrow and Tipler have a book on the anthropic principle, so they describe probabilistic considerations there. Carter does it himself in 1983. Here is a Bayesian account of what the weak anthropic principle is doing and the way in which the selection effect is operating. Let's just think about it, analyze it, and see how it might relate to these considerations as they relate to the effective observation principle. T sub D is Dirac's non-standard physical theory, where G goes as 1 over T. T sub B is the standard Big Bang model of cosmology. If you set aside anthropic considerations, period, so you don't take them into account, then ask yourself the question, what is the probability of this coincidence given Dirac's theory? What is the probability of the coincidence, this equation, that equation, this equation, given Dirac's theory? Given that Dirac designed this theory such that this equation would be true. Answer? Well, okay, this, right? Fine. What is the probability of this coincidence given the standard Big Bang model of cosmology? Those of you who shook your head when I said, do you expect those two sides to be similar, would argue for this, right? What you in fact did, maybe, if you're thinking probabilistically, is express this, but with a head shake. So then, using Bayes' theorem, assuming equal priors, you find that Dirac's theory is overwhelmingly favored. Just so that we're on the same page, a posterior distribution for Dirac's theory given the coincidence, the ratio of that to the same kind of entity for the Big Bang model of cosmology is the ratio of the likelihoods times the ratio of the priors, and the ratio of the priors are 1, as I assume them to be equal. So Dirac's theory is overwhelmingly favored. Okay, so now here is what you could do and perhaps ought to be doing. In the presence of anthropic considerations, let's consider it conditionalized on the proposition that life such as ours exists now. Now our total evidence is not just the coincidence, but is the coincidence and the proposition that life such as ours now exists. Then you use Bayes' theorem, again, which tells you that the probability of Dirac's theory given our total evidence over the same thing, but for the standard Big Bang model, is given by the ratio of the likelihoods. Ratio of the likelihoods times ratio of the priors. Ratio of the priors goes away. I'm assuming equal priors. Standard product rule for probabilities then gives you this decomposition that the ratio that you're interested in is given by the ratio of this kind of a likelihood, namely the probability of the coincidence given life and Dirac's theory over the probability of the coincidence given life and the Big Bang theory, multiplied by a ratio that consists of the probability of life given Dirac's theory divided by the probability of life given the Big Bang theory. Okay, so point number 1, these terms are all 1. So why? Well, okay, there's a good question as to why, but if you stare at these two terms and ask yourself, what is the probability of life existing now in Dirac's theory compared to the probability of life existing now in the context of the standard Big Bang model of cosmology? Is it very different? Are these very different? And plausibly, they're not very different. The probability of life existing now, if it's not very different in these cases, we can set this term to 1. And this particular piece here, I can't highlight it, this particular piece here is what Carter's calculation made very plausible. The probability of the coincidence, that large number coincidence given the Big Bang model, and the fact that we take into account life, and the fact that we take into account the idea that there is life around, quote unquote, makes this probability very high. In fact, deduces it at some level. And this is always 1. This numerator was always 1. Dirac's theory was intended to account for this, and life is not going to spoil that, hopefully consistent with it. So, so both of these terms are high, and both of these terms are close to 1, and so the ratio is close to 1. So everything is unity on the right hand, order of magnitude, unity on the right hand side, and so Dirac's theory is no longer favored by this calculation. So just to summarize this analysis, what happened when we didn't take into account the selection effect was that the Big Bang model of cosmology was not favored. The posterior distribution of the theory, given the evidence that we have, which was the coincidence, was significantly smaller than for Dirac's theory. But then we went ahead and conditionalized on the proposition that life such as ours now exists, and the posterior distributions both became so this distribution became larger in such a way that it tracked essentially this term over here. Essentially this term over here. So then you avoid the need for the non-standard theory. You don't need to posit it anymore. Question. Well, okay. So let me point out one thing. I think this argument works. I think it qualitatively works, right? It works. Let me ask another question, and that is about how well defined is this line of reasoning? How quantitatively precise, from one point of view, can you make this line of reasoning? Let me cash that out in terms of a particular distinction. So these key distributions, this likelihood here, and this likelihood here, these are certainly, I think, least subjective when it's the case that this quantity L can in fact be described in terms of our theory, that it is expressible in terms of our theory. If it isn't, the question is, if you cannot take life and express it in terms of a theory of interest and computing this kind of a probability, the question is, how do we understand and compute these probabilities? That's one question. The other question is, that relates to how well defined this line of reasoning might be. The other question is, if you look at this ratio, we're really, in fact, in trying to compute this ratio, you're comparing these two quantities. And the question is, how well defined is this comparison? And the thought is that if the notion of life, the sense in which these theories refer to life, the way in which you would understand the notion of life in each one of these theories, if it's the same, then this comparison makes sense. If it's not the same, then there's a question as to why you can in fact compare these two probabilities, take their ratio, and then take the output as something that can enter into a Bayesian calculation. I don't think the second issue is an issue. I don't think the notion of life in the context of Dirac's theory or the notion of life in the context of Big Bang theory is obviously different. And so I don't think this poses a problem. I think the issue arises to some degree in thinking about this first problem. And the thought is that for neither theory is it the case that the notion of life is expressible purely in terms of the cosmological theory. The dependence of the concept of life in each theory is thus unclear. This, I think, threatens the objectivity and how well defined may be the probabilities, such as P of L given T. Does this undercut the argument? No, right? Qualitatively, I think it works. I think there's a question of how well defined these various entities might be. All right, there's two ways forward. You can interpret these probabilities such as P of L given T subjectively as credences of agents or assessing a cosmological theory. This is available to you. If you want to try to be more objective, if you want to try to connect our notion of life to the theory of interest, well, you're going to have to append theories to the cosmological theory. You're going to have to append theories such as astrophysics and maybe astrobiology and biology to this theory of cosmology to try to get a handle on what it is that the theory can in fact tell you about this thing L. And there's some matching that is required. In standard effective scenarios and the tried and tested effective scenarios, this matching is well defined. There's prescriptions for doing this. And thinking more broadly about effective theories, it's not clear to me that those prescriptions are available to you. They're in fact not available to you. And so you have to try and figure out a way to do this matching. Fine. And such matching presents a hurdle because, as I say, the technology as it were, is not there. And also it's the case that our theories of life are relatively underdeveloped. So this is going to cause a problem as well. All right, so let me summarize this point about the probabilistic analysis to be clear about where I stand on this. There are issues faced by probabilistic applications of the anthropic principle that are very closely related to the concerns raised in the non-probabilistic analysis that I described earlier. The anthropic principle makes reference to an entity, namely observers or life, that cannot be uniquely interpreted in the context of the theories within which the anthropic principle is meant to be understood and applied. In probabilistic cases, this ambiguity in what could be meant by observers pushes back against the objectivity of those probabilities. And insofar as it does that successfully, it undermines the arguments that rest on these comparisons. Quantitatively, I don't think qualitatively. Right, so how does the effective observation principle help? According to the effective observation principle, we are compelled to restrict attention to entities, namely these deltas, that are in fact expressible in terms of the theory, The recommendation is to choose a candidate that is expressible in terms of the theory, and two, so one is expressible in terms of the theory, and two is as specific as possible about our observational situation. This choice renders the underlying reasoning well-defined, whether it is probabilistic or non-probabilistic. Okay, the problem is, of course, still, as I've mentioned, how you go about picking out a suitable delta. And in probabilistic situations, the issue remains as to how to go about computing those probabilities, period. Nonetheless, I think the question is well defined. And there is a target of our analysis, this observational situation. Fine. And then, just as I described in the context of non-probabilistic situations, when estimates are made for probabilities of life, what is actually being employed as some proxy for life for observers. What has been identified in these applications is an end, and not just in the example from Roman that I was describing, but in other examples too, such as in Carter in 1983. What has been identified as an entity such that were it to obtain, observers like us might arise as an accident, but where that entity doesn't refer to observers in some essential way. Namely, some version of the effective observation principle has been identified and applied. Caveat. Okay, so it's not that the effective observation principle evades the hurdle that's faced by the anthropic principle, wherein matching of theories is required to more closely connect delta to the concept of an observer. This concept, I think, is better schematized by the inclusion of biological and chemical considerations. So you still have to figure out how to do it. I think it's an open problem. I think it's an open problem in trying to make sense of the claim that these other theories outside of the tried and tested way, the tested ways in which we think about effective theories are effective. This kind of a scheme needs to be made sense of, and if you can make sense of that scheme, you can address this kind of issue in the context of the effect of applications of the effective observation principle. The hurdle is made manifest in the effective observation principle. That's the point. The effective observation principle provides conceptual clarity, and it describes some specific or non-algorithmic tasks, namely one, get your observational situation to be expressible in terms of the theory, and two, have it be specific as possible about your observational situation. That might help to facilitate appropriate applications of anthropic style reasoning in scientific practice. It might help to yield better estimates for what we can expect to observe. Okay. I think there are limits to this kind of reasoning. I think ultimately you can try to be too specific and you're not going to do much better. You might end up with a kind of plateau in terms of how well you do with regards to precision as you add more data. So, okay, that's another caveat. And then I think furthermore, these considerations can make failures of anthropic style reasoning more conceptually transparent as for one of these two tasks is not adequately completed. If your characterization of your observational situation isn't written down expressly in terms of the theory, and or it's not super specific, then you may fail in your attempt to apply this principle in some setting. All right. So in the last few minutes, I want to take us beyond cosmology in the following way. Anthropic style reasoning can be applied, it has, in very different contexts, such as in particle physics and astrobiology. Barrow and Tipler have a book with two extensive chapters where they claim to apply the anthropic principle in lots of different settings. There's a question as to whether they're applying the principle or something else. I think there are certain cases where they definitely do apply the anthropic principle. And so you can read about it there. And what I want to do is provide some general remarks. I think this principle can be applied in a more local sense whenever observers are part of a subsystem that is effectively isolated from its environment. And then what we can expect to observe corresponds to observables in that subsystem. The effective isolation should be understood as a decoupling of some kind between the system and the environment, so that any effects the environment may have on the subsystem can be described in terms of degrees of freedom of the subsystem. And then there is a theory in the background. There's a question of precisely what theory should you be using in looking to constrain variables in the subsystem by virtue of thinking about the notion of an observational situation in the context of that subsystem. Well, that theory is going to match the kind of subsystem of interest. So if we're interested in a cosmological parameter, then the theory will correspond to a cosmological theory, possibly coupled to an astrophysical theory. And it may be that other further theories downstream, such as astrobiological or biological theories, neuroscientific theories, will be irrelevant. For there is in many such scenarios an effective decoupling of such theories from cosmological theories, assuming we can make sense of that notion effectively. The parameter of interest is more local in nature, one that relates to a terrestrial phenomenon, one that relates to I think physics setting. Then the theory is going to be geophysical in character, or it's going to be more of a nuclear physics theory. In which case we can set aside our concerns about cosmological theories and or astrophysical theories. This conclusion, this thought that one can in fact go beyond cosmology is consistent with something Carter said in 2006. Carter says AP, the anthropic principle, is not intrinsically cosmological, but just as relevant on small local scales as at a global level. This insight applies to, Carter didn't say that. This insight applies to EOP as well. Okay, so let me summarize. Let me tell you what I've tried to bring into focus. So unlike Carter's version of the anthropic principle, the so AP, the weak version and the strong version, EOP is again a selection. So sorry, it is like Carter's anthropic principle in the following way. It is a selection principle. It is an observation selection principle. It is distinct from Carter's version of the anthropic principle in that it makes explicit the focus of such principles on observational situations and not on observers. And it does so relative to an explicitly acknowledged theoretical context, which I think furthermore is an effective theoretical context, understood very broadly. This observational situation is characterized by an entity, which I've been calling delta, that is instantiated by a set of conditions that are, as I said, theory dependent. And this focus on an observational situation is important for the phrase, our presence as observers cannot be unambiguously understood in the context of our best physical theories. So EOP is consistent with our understanding of the scope of our effective theories. Furthermore, I think the effective observation principle, this way of rethinking the anthropic principle, can be broadly applied. The traditional pattern of anthropic style reasoning, as it's been employed in cosmological scenarios, as well as in more local settings, this traditional pattern, I think, is really precisely described as an application of the effective observation principle. And then a challenge, other than the challenges that I mentioned in making precise the notion of delta and connecting it to a notion of effectivity, as it were, writ broadly. Challenge, while we can characterize general features of delta, delta is an algorithm that gives you an optimal delta in any particular situation. And the question arises as to whether there are heuristics for determining more relevant deltas and whether that can ever play a useful role in our theorizing in the way that it might have played in the past, as Carter described for us in 1974. Okay, that's it. Thank you very much.
We'll take a 2-minute break so that we can refresh ourselves.
Yeah.
The UCJ is conditionalized on what to expect. Not necessarily
That's what I'm trying to do.
which doesn't necessarily mean the exact